Hey everyone, it's Mr. Huff,
And Miss McConnell.
and this is going to be that video that I was talking about at the end of class that's going to help us finish up looking at help us finish up analyzing and comparing the logarithmic function with its inverse. So, like I said, a lot of us in class were getting to this 2 to the x, and I just want to make sure that we have a fully formed idea and a few strategies by which we can justify and convince ourselves and our neighbors that this 2 to the x is the inverse function to this log base 2 of x function here.
One note is that you are going to see all of the log base 2 of x functions in blue. So anything that's in blue, including the table and then the part of the graph that's blue, and then what's written in blue, that applies to the logarithmic function, whereas the green specifically applies to the exponential inverse part of it.
Mm-hmm. Okay, so in the past we've looked at inverses and we came up with a few things for inverse relationships. The graph is reflected across the y equals x, or the x equals y line. The xy coordinates on the graph itself. So for instance, this is at 8, 3, so the inverse point to that would be 3, 8, and so if we go over 3 and we go up to 8, we'll see that we land there. Table columns are switched, and so what that would mean is this x, y, these two things will be for the inverse will be switched, and we would be able to then use these as our inputs in our inverse function, and we should get the previous inputs out as outputs. And so just to really make sure that is clear. Okay. Why is it? Okay, and so we have x, y, y, there we go.
It's when you're resting your hand on it.
I'm not resting my hand on it though. Whatever. So let's take 1, 2, and 3, and we'll. Oh my god.
Okay, so we have 1, 2, and 3, and then we are looking at an x, and then we have our f inverse of x.
And so we want these 1, 2, 3 x's to be used in our f inverse, and they should generate the previous inputs we had for f of x. And so we have the previous outputs 1, 2, and 3, and we have then previous inputs of previous out. Okay.
You're fine.
I'm just gonna wait for you to finish so I can start talking about it. Let me use that as a pointer.
Oh, sure.
So we took these as our previous. These were our previous outputs. Changed them into our previous inputs for the inverse comparison, and then we use these inputs in what we are hoping is the inverse function, and we get 1, 2, 4, 8, which were the previous inputs from before. Now, one of the last things that we can do is a composition, and you may think that the composition is going to be complicated, but in reality it's a lot simpler than you would give it credit for. So we have f of x. Yeah, I see. Yeah, you're better at it. So we have, I will compose them, right? We've looked at composition before, not making a difference as to which order we're composing them in. And so in this case, we will compose f of x, which is log base 2 of x, with our inverse, which is then 2 to the x. And so now we have log base 2 of 2 to the x, and we are going to say that that is equal to y, right? So that we can rewrite it and readjust it. And so now from here we can use an equivalent form to kind of break out that that 2 to the x, and so we can figure out what it is exactly.
Or you could use the power property.
Or you could use the power property.
Yeah, actually, you could use the power property to say, all right, well, I have this 2 to the x power. I know that that's going to be equivalent.
Oh, yeah, that's even better. It's even more efficient.
So it's going to be equivalent, and I'm just going to switch to black since I'm working with these two functions. I've set them up. Then I get log base 2 of 2. You should be thinking 2 to what power equals 2? Those are undoing each other in a sense, and when they undo each other, you're just left with 1 times x. So when you compose these, then you get x by itself. Similarly, we could compose the f of x with as the input here.
And we would get 2 to the log base 2 of x.
Exactly. So you would get 2 as the base of your exponent, and then
to the 2 there.
Yeah, and then your
Log
input.
Base.
Yep. Your input would be log base 2
of x.
And then you see you have this, what's actually called exponentiating, when you have this base 2 and then you have the log base 2 here. So this base 2 exponential and the base 2 logarithm, they undo each other, and you're left with x.
And I think one of the last ones that we can use to analyze this, that someone in my class specifically looked at, they considered taking log base 2 of y is equal to x. So they took this idea of switching places and switching the x and the y, and they did this, and they said, well, I'm just going to resolve this for y. And so they used an equivalent form to get to 2 to the x equals y, and that was their justification for that being the inverse. Oh, I should make it green, huh? To make it 2 to the x is equal to y. And so there were, five different ways?
Yeah.
5 different ways to look at and justify that we know that 2 to the x was in fact, or is in fact, the inverse to log base 2 of x.
Yeah. So one thing that we really want you to notice about the key features here, when you're talking about intervals of increase and decrease, what you'll actually notice here is that it's the exponential function is increasing across the entire interval, and so is the logarithmic function. The logarithmic function is also increasing across the entire domain, and so then you'll notice that it is increasing across the entire interval. And what you'll notice in the exponential function is that the rate of change slowly starts to pick up over here, where the rate of change itself is increasing, and then it just skyrockets off. So we notice that in the logarithmic function, the skyrocketing rate of change increase is happening when x is really close to 0. And then as you get farther out on the x-axis, then you're seeing a really small amount of change, because you're noticing here that for every 1 increase in y, you're having to go farther and farther and farther in your x values to get that 1 increase.
And let's see. Oh, the other thing too to notice for these intervals of increasing, notice this is more of an extension to it, but notice that these, like she said, are both increasing, but they have distinctly different shapes. This one's more of a cup, this one's more of, I don't know, just kind of rounds over. But they are both increasing, and so this is not a minimum and this is not a maximum. Because if we look at a very localized point, we never get a change in direction. We never get a value. We never get a y value that's around any of these points that will be less than. Every y value is always increasing. Every y value is always increasing. And so that is just another part of the key feature analysis.
Now, one thing you should notice about the logarithmic function is that the domain is from 0 to infinity. What we noticed is that we cannot input any x value that is going to output anything, because when you're thinking to yourself, you know, when you have your logarithm, you're saying 2 to what power equals some negative number. That's not possible. So we noticed that the domain is from 0 to infinity, whereas in the exponential function, you could input any x value, and the range ended up being restricted to be 0. We had a horizontal asymptote there at y equals 0 in the exponential function. And so our range actually became restricted. So again, we see that x and y values are switching places from one function to its inverse. So now we'd like to go ahead and talk about number 2. Yes?
I guess. I was done.
Okay. So, you don't want to continue with number 2?
Not on this video.
Oh, okay. Yeah, actually, that is a good point to go ahead and pause this video. All right, so we will go ahead and stop the video here.